Hello Metrics Nation, I am excited to introduce the penultimate chapter in our econometrics course, the chapter on binary dependent variables. Let's go ahead and jump in. In today's lecture, I am going to introduce the idea of these binary dependent variables, and in particular talk about the most straightforward way to estimate them, that is using a linear model. So this is simply an introduction to this topic. Binary variables we've seen before, they're either 1 or 0. They are an outcome that either happens or it does not. You either pass econometrics or you do not. Your test result for COVID-19 either comes back positive or comes back negative. So like I said, we're going to talk briefly here about the linear probability model. This uses the technique that we have talked about the most, ordinary least squares, to estimate the relationship between that binary dependent variable and other independent variables, other causes. So we could look at your passing of econometrics and see how study hours plays in. We could see how the difficulty of your other classes plays in. In this context of a linear probability model, the predicted values, the things that we've used as y hat, are not predicted values in the terms of passing or not passing. These will not be either 1 or 0. These will not be dichotomous predicted values. Instead, we interpret these predictions as predicted probabilities. So it's the probability that you're passing. In turn, the coefficient estimates that we look at, we think of as being predictions about how probability changes with a 1-unit change in x. So how the probability of passing a class or the probability of any dichotomous outcome would change with a 1-unit change in the corresponding x variable. Now, the example that I typically use to motivate this is an example from sports. And cut. Now, what we're going to focus on in this lecture are some of the pros and cons of the linear probability. The downsides are that in a linear model, x has a constant impact. So the impact of x on the probability will not depend on previous values of x and will not depend on the underlying previous probability. Therefore, our predicted probabilities are not going to be bounded between 0 and 1. The estimation technique is going to be susceptible in a very predictable and consistent way of how it deals with outliers, and our errors are not going to be normally distributed. They are actually going to be quite heteroscedastic. However, linear probability models are very good in that the coefficients are very easy to interpret. It's hard to mess these up and get them wrong, and it's also, for the relevant values of x, the fancy techniques that we're going to talk about that are not the linear probability model often show a very similar relationship to the LPM. So usually to motivate this chapter, I introduce this idea of the spread and talk about some upcoming sporting event. Usually I send out a survey asking students what they think will happen in the game. However, we have no upcoming sporting event. And so I'm going to use an old sporting event and data from previous classes on their beliefs. So we're not just going to look at who's going to win or lose, we're actually going to take this idea from sports betting of the idea of the spread. So to keep it interesting, they bet not only who's going to win, but on how much a particular team will win by. So for example, let's consider a football game where the Patriots and Giants are playing. And let's say that the Giants are favored by 3. Now that 3 is the spread. They need to get more than that in order to beat the spread. if you bet on the Giants to not only win, but to beat the spread, but the Giants win by 2, you actually lose. You lose that bet, the Giants still win. Your choice to bet on, whether or not to bet on the Giants covering that spread, assuming you are betting, is going to depend on the spread. And that's how we're going to think about this example here. We're going to have our y, do you bet on it, and our x as to whether what exactly the spread is. So let y be 0 and 1, a binary variable, to be if the Patriots are beating the spread. X is going to be the spread between the Giants score and the Patriots score. If X is positive, the Giants are predicted to win. If X is negative, the Giants are predicted to lose and the Patriots are predicted to win. So thinking about the extreme values here, if X is all the way out to 100, meaning that in order to do this, the Patriots would have to win big. They'd have to win by 100 points. Almost everyone is going to choose 1. The Patriots would never lose by 100. If X is negative 100, where the Patriots are going to win, almost everyone would choose 0, because the Patriots would never beat the Giants by that much. So here is the data that I got back, or a portion of the data, when I ask about who would win and by how much. Now this implicitly defines which spreads the students, whose names are hidden to protect the guilty, how much they would bet for or against the spread. Now let's look here at a scatter plot. This is just a regular scatter plot. It's fairly useless. What we can see is it's hard to tell. These all look like they are one single individual. It looks like there are just as many up top here as there are down below. That's because the scatter plot, the dots are stacking right on top of each other. As a note for your final project, when you have a binary variable and you're trying to scatter, doing a regular scatter plot does not show what you're interested in seeing in terms of seeing the densities of around those points. So what I have done here is show not just the density, but I have varied based on how many are there. I've spread these out a little bit. And so we can see that there are a lot more thinking that the Patriots would win than there are up here. So a couple things I want to point out on this graph. So what we can see is that almost everyone, once we get around 20, thinks that the Patriots cover the spread. I think I misspoke earlier. Down here is the Giants. Takes a little bit longer. So what we're seeing is a situation where the Patriots in this example are favored. What we have here is a simple linear regression. So it's a linear probability model because our outcome is a binary variable. This red line is the fitted slope here for this regression. How we'd interpret this coefficient is that every change in the spread, every increase in the spread, increases the probability of someone choosing this team by 1.76%. That's how we would interpret it. It's very straightforward. We also can see some of the cons of the linear probability model. These are your predicted probabilities for any given spread, the predicted probability. We can see that the predicted probability goes negative after around the spread going less than 30, negative 35 here. And it gets greater than 1 once we pass approximately 20. That is not a desirable property to have predicted probabilities outside the range of probabilities. Probabilities are defined between 0 and 1. Another undesirable characteristic is, what if we had just not included these more extreme values? We had somebody who sort of put, I think, 40 for how much they thought the Patriots would win by. That's what's going on up here. What if we hadn't included these values? How would that impact our regression result? Now, for the most part, especially once we got beyond 40, everyone is doing what we would think. Everyone is saying that the Giants would cover that spread, that the Patriots wouldn't win by 40 or 45 or 50. And we might think that the fact that these are included and people are doing what we would expect, it would perhaps strengthen the relationship there between y and x. But generally that's not the case. We have this linear slope. So as you add more observations here and extreme values, the slope actually gets narrower. So let's look at how it is with only between the two 30s here. So what we see is, instead of that 1.7 or whatever it is, we have a higher value. We have a 2.4% slope. So the impact of a 1 unit change in the spread is higher. All we did is remove those extreme values. Right? So with the extreme values, we had a slope that looked more like this. It was less steep. So that is another undesirable property of using the linear probability model. Another view that we can use to help us characterize the relationship between x and our outcome, so we looked at the scatter plot with the jitter, is to look at the averages as we move through the values. And in particular, we could pick bins. If this is a truly continuous statement, we could look at the averages at different areas. So what I've done here is, this is simply the averages at every point, because it's discrete points. And we can see how this particular setup, the average is monotonically increasing. We're down at 0, and then we have that one person who between 40 and I think 18, there was only that one person. And then we slowly start to pick up, and then it changes very quickly right around a spread of 5, and then changes a little bit more slowly. And then what we have up here is that the increasing the spread, everyone is at 100. Let's take one more view at this, just smoothed out. It's the same view. We're going from probabilities where everyone is not picking it to where everyone is picking it. And I'm going to once again overlay that linear estimation, that linear probability model, and talk about how it misses some of the things that we're interested in. So as a linear model, the impact of a 1 unit change is the same whether you're down here in the 50s, down here right around 10.5, or whether you're up here in the positive 20s. So moving from a spread of -8 to -7 in the linear probability model has the same impact of moving from -47 to a spread -46. Right? But we can see in our data, and we can think logically, that this change isn't going to have much of an impact. A 1 unit change, when we're definitely not going to pick the Patriots to cover, isn't going to have much of an impact. Likewise, when we're definitely going to choose them, it's not going to have much of an impact either. What we would expect is in the middle here, and that's what we're seeing in our data, in the middle here a 1 unit change is having a big impact. So what we are going to want to introduce is a model that gives us different marginal effects, different changes in probabilities for a change in x, depending on where we are in our probability. If we're right in the middle, or we're not sure if we're going to go with the Patriots or the Giants, that 1 unit change is huge in terms of the change in probability. But if we're already positive, or already certain we're not going to, that 1 unit change really isn't impacting much. It's those people in the middle that are really impacted by a change in x. And what we're going to introduce is the probit and logit models that have that functional form. So overlaid in gray is the logit function fitted to this model. And we can see that it has some certain properties. It's bounded between 0 and 1. That is going to be one of the properties that we like about that model. We also can see that the marginal effects are very small. They get larger, they're biggest right around where that sort of decision point is happening, and then once again they get small. The final problem with the linear probability model that I'm only going to mention very briefly is this problem of heteroscedasticity. We know that the errors, the difference between the linear estimates and the actual values, are going to vary in a predictable way. They are going to be related to x. And furthermore, they're not going to be normally distributed. The thing you have to do is you have to make sure that you include robust standard errors whenever you're using a linear probability model. That's it for our very brief introduction into binary independent variables. I hope you're all doing well, hanging in there, and I hope to interact with you soon. Take care.